Welcome you all to the fourth session of Special Theory of Relativity of 5th semester BSc. I am Sunil MH, Assistant Professor of Physics in Government First Grade College, Annalinur. In this session, we are going to study the Lorentz transformation equations, which are different from Galilean transformation equations, which was studied in the first session. Here, the man who's standing beside Albert Einstein is the Lorentz, one of the greatest physicists who brought these transformation equations, and Einstein used those equations to prove many things in special theory of relativity. These are the things we need to require before going to the session are frames of references, dynamics of the system, Galilean transformation equation, which we were studied in the last sessions. The Lorentz transformation equations are the equations introduced by physicist Lorentz. These are the transformation equations which are consistent with the concept of the invariance of light velocity in free space, whereas the Galilean transformation equations are inconsistent with the invariance of light velocity, because we can add or subtract some velocities from velocity of light in Galilean transformation equation. That is, the velocity of light was not independent in Galilean transformation equation, but Lorentz made a correction in these things and he brought these transformation equation which are very much consistent with the constancy of speed of light. Derivation of Lorentz transformation equation. Let us consider two frames of references S and S prime with coordinates x, y, z and x prime, y prime, z prime respectively. The S prime frame moving with a constant velocity v with respect to S frame. At time t is equal to 0, the two origins of S and S prime, that those are O and O prime, coincide each other. We take O and O prime as two observers. At the time t is equal to 0, when the two frames of references are coinciding, a light pulse has been initiated at the origin. After a lapse of time, that is after a time t, we take that time as t, the observer at O saw that the light has reached the point P having the coordinates x, y, z with respect to S frame, x prime, y prime, z prime with respect to S prime frame of reference. P is a point at a distance x from the origin of S frame, and here we have taken a small r, which is a distance from the observer at O to the point P. R prime is the distance of the observer at O prime to point P. X prime is a distance of point P from this S prime frame, and VD is the distance between the two frame of references. V is the velocity of the S prime frame moving with respect to S frame. So some of the things we have with this picture are S prime frame is moving with v velocity v with respect to S prime. O and O prime are two observer coincide at t is equal to 0. coordinates of events at P with respect to S frame are XYZ, with respect to S prime frame are X prime, Y prime and Z prime. The distance of P from O is R, that is equal to C into T. R is the distance between the point P and the observer O is equal to the velocity of light C and the time T, where using the geometry we can write R square is equal to X square plus Y square plus Z square, which is equal to C square T square. The distance of point P from the observer O prime is R prime, which is equal to C into T prime, where R prime square is equal to R x prime square plus Y prime square plus Z prime square, which is equal to C square T prime square. When the time T is equal to 0, these two are equal, that is R square is equal to R prime square. We are going to use that condition here. That is, since both observers O and O prime are at the center of the same expanding wavefront, we can write R square is equal to R prime square, or x square plus y square plus z square minus c square t square is equal to x prime square plus y prime square plus z prime square minus c square t prime square. Since there is no motion along the x and y and z axis, y is equal to y prime and z is equal to z prime. In both the sides, in LHS and RHS, y and z cancels out. The remaining thing, x square minus c square t square is equal to x prime square minus c square t prime square. So the transformation equation which relates between x prime we can write as x prime is equal to k into x minus vt, call this as equation 2. Similarly, for time we can write t prime is equal to a into t prime minus bx. Here, this is the transformation equation between x prime and x. This is the transformation equation between t prime and t. Here, a, b and k are constants. We need to find those constants, values of those constants. Substituting the values of x prime and t prime in equation, or substituting the values of 2 and 3 in equation, and solving, we get this equation: x square minus c square t square is equal to k square into x minus vt whole square minus c square a square into t minus bx whole square. Simplifying, after simplification of this equation, we get x square minus c square t square is equal to k square minus c square a square b square into x square minus 2 of k square v minus c square a square b into xt minus of a square minus k square v square by c square into c square t square. Compare LHS and RHS. We have coefficient of x square 1 here, and here coefficient of x square is this thing, k square minus c square a square b square. Here coefficient of xt in the RHS, coefficient of xt is this thing, minus 2 of k square v minus c square a square b. Here the coefficient of xt is 0, whereas the final thing, the coefficient of c square t square is minus 1 here. Here the coefficient of c square t square is minus a square minus k square v square by c square. So equating the coefficients of x square, xt and c square t square separately, we get these three equations. One is k square minus c square b square a square is equal to 1, k square v minus c square a square b equals to 0, and a square minus k square v square by c square is equal to 0. And solving these three equations to find the constant k, a and b, we get k and a are equal things, which is equal to 1 by root of 1 minus v square by c square. This is the most important parameter in whole theory of relativity, and the value of b is equal to v by c square, where v represent the velocity of the frame of reference moving with respect to inertial frame of reference, and c is the velocity of light, which is constant. Substituting these values in equation 1 and 2, we have transformation equation, that is x prime is equal to k into x minus vt, and t prime is equal to k into t minus vt. So substituting these values means substituting a, k and b in those equations, we get x prime is equal to x minus vt by root of 1 minus v square by c square, and t prime is equal to t minus vx by c square whole divided by square root of 1 minus v square by c square. So then we can write the Lorentz transformation equations are x prime is equal to x minus vt by square root of 1 minus v square by c square, that was derived here. Y prime is equal to y, z prime is equal to z. Since there is no motion along y and z axis, they keep as it is. Y prime is equal to y and z prime is equal to z. And the fourth coordinate, that is time, t prime is equal to t minus of vx by c square divided by square root of 1 minus v square by c square. So those are the Lorentz transformation equations. The inverse Lorentz transformation are gettable by the coordinates and replacing v by minus v in the Lorentz transformation equation. That is, we get inverse Lorentz transformation equation by interchanging the coordinate x to x prime to x, and v by minus v, replacing v by minus v. That is, x is equal to x prime plus v into t prime divided by square root of 1 minus v square by c square, y is equal to y prime, z is equal to z prime, and t is equal to t prime plus vx prime by c square divided by square root of 1 minus v square by c square. These equations convert measurement made in s prime frame into those in the s frame. These are the Lorentz or inverse Lorentz transformation equation. So we are going to show when the velocity of the particle or a body is very much smaller than the velocity of light, that is c, that v is very much smaller than v, Lorentz transformation reduces to Galilean transformation. Here v is the velocity of any particle. So consider the Lorentz transformation equation we have derived here, that is x prime is equal to x minus vt by root of 1 minus v square by c square, y prime is equal to y, z prime is equal to z, and t prime is equal to t minus vx by c square whole divided by root of 1 minus v square by c square. These are the most important equation in special theory of relativity. So considering these three equations, let take a condition when v is very much smaller than c, v by c, the value v by c, the ratio v by c tends to 0 as c increases and v reduces, the value nearly goes to 0. Then we can get this term, that is 1 by root of 1 minus v square by c square. This nearly goes to 0. 1 minus 0 will become 1. Root of 1 is equal to 1. 1 by 1 is equal to 1. This value nearly equal to unit. So we can write the Lorentz transformation equation becomes, means in this equation x prime is equal to x minus vt, the whole term, this term, the term inside the square root become 1, therefore we get x prime is equal to x minus vt. Y remains as it is, Z remains as it is, and T also, here T also, V by C square reduces to reduces to or tends to 0, T minus 0 become T, and the denominator become 1, so T prime is equal to T, which are not Lorentz transformation equation, those are nothing but Galilean transformation equation. With this we can conclude that when the velocity of the particle or a body is very much lesser than the speed of light, then the Galilean transformation equation reduces to, the Lorentz transformation equation reduces to Galilean transformation equation. So in this session we have studied importance of Lorentz transformation equations, derivation of Lorentz transformation equations, derivation of inverse Lorentz transformation equation, reduction of Lorentz transformation equation to Galilean transformation equation, and advantage of transformation, means the Lorentz transformation equation over the Galilean transformation equation. Galilean transformation equation cannot be used for the to study the special theory of relativity, where the second postulate says that the velocity of light is constant, whereas in the Galilean transformation equation the velocity of light is not constant. So this is the advantage of Lorentz transformation equation over Galilean transformation equation. With this I put an end to this session. Some of the reference book we can go through these to study the special theory of relativity. Thank you all.